Welcome everyone. I see some new faces, so welcome those coming here in person, and welcome all those on Zoom watching us from online. Today we have the pleasure to have Bjarne Schülke coming all the way from California. So he's from Caltech, and he will teach us something about hypergraph Turán problems. Okay, let's welcome.
Thank you, Hong, for the invitation, and welcome all to the mini course on Hypergraph Turán. So we'll start pretty basic, and also in 1 week time, I guess we cannot get to the very sophisticated methods that we've seen in the recent years. But maybe even if you already know something about Hypergraph Turán, this will be a good repetition sort of the basics. So generally in extremal combinatorics, we are interested in the threshold behavior, right? So we have some discrete structure like a graph or a hypergraph, and we look at some parameters. So this can be the minimum degree, it can be the edge density, and we ask what happens when like how large does this parameter have to get so that some behavior changes, so that we have some property or that some property stops being true. Okay, so some examples. For this, our direct theorem in graphs, right? So this tells us the minimum degree condition that guarantees a Hamiltonian cycle. And another example would be the Bjarne-Schülke theorem. So let's just say ECOPRO. So this tells us how many edges we need to have for a family to stop being intersecting. So this is the maximum number of edges for some family of k-sets. That is intersecting. Okay, and then what we want to look at is a generalization of Turán's theorem. So Turán for graphs tells us what is the maximum number of edges in some graph on n vertices that doesn't contain a clique of a certain size. So in KR3 graphs. Okay, so all these are really classical examples for the kind of theorems that we are interested in extremal combinatorics. And so arguably, this is one of the most natural questions. And what we are interested in is what can we say for hypergraphs? So what is a hypergraph? So instead, we start very basic. So a hypergraph H consists of vertex set B and an edge set E, which is just a subset of the power set on B. And mostly we are interested in uniform hypergraphs. So H is K uniform. And often we just say a K graph. If every edge is of size K. So the size of every edge is K. Okay. And so now for these generalized structures, right? So if our K is 2, then these are just graphs. And for these, we can just define the extremal number and then the Turán density in the very similar way. So as we do it for graphs. So given the K-graph F and some natural number N, the extremal number N, which we denote by X and F, is the maximum number of edges in every K-graph on n vertices. Every K-graph on n vertices. Okay, and F3 just means that we don't contain a copy of F. And so often we are mainly interested in the asymptotics of this. And so the asymptotics here, we want to think of it as density. So we divide this extremal number by the number of the maximum possible number of edges. So n choose k. So the Turán density of the K-graph F is pi of F, which is the limit for n going to infinity, the extremal number of n and f divided by n choose k. Okay, so now the first question is this limit even well defined? And of course it is. So this may be an observation. Density always exists. That this is well defined. This limit exists. Every okay, so let's see. So what we want to argue is that the sequence of these fractions is non-increasing. So we will show that this is greater or equal to this. And then, so this means that we're the sequence is non-increasing, but also clearly we are bounded from below by 0, right? Because this extremal number is always at least 0, and therefore we will have that this sequence converges. So. Okay, so how do we argue this? Given n and k graph H on n vertices, and so we want to bound this extremal number. So let's say that we have more edges than this times this. Okay, with this lowercase e of h, I just denote the number of edges in h. So the size of e of h. So let's say that this has more edges than this previous fraction times and we want to argue that such an H always must contain a copy of F. Okay, and for that, so we somehow need to make use of this extremal number, meaning we want to find some set of n vertices such that the number of edges of H induced on this set of n vertices has more than this number of edges.
Then you mean H has n plus 1 vertices.
Oh, sorry. Yeah. N plus 1 vertices. Okay, so by averaging, you get. So let's look at summing over all vertices of H and looking at the number of edges in H where one vertex is deleted. Okay, so how often do we now count every edge in H? So we counted every time when so for all vertices when X is not in our edge, right? So we get the number of edges of H, and then n plus 1, so the number of vertices of H minus the k vertices for which we have which are contained in that specific edge. So minus k. Okay, so this is by double counting. And so this thing now, because of our number of edges in H, we know that this is n plus 1 minus k times the external number F divided by n choose k times n plus 1 choose k. And so now let's divide by n plus 1 and that implies that for 1x, this number is larger than this thing divided by n plus 1. So by averaging, we find that for 1x, this graph obtained from H by deleting x, which is a hypergraph on n vertices, has more edges than the extremal number for n vertices. So by definition, this means that that H minus X contains X. Okay. Any questions so far? So just feel free to ask questions at any point. Okay, so we know that this number is well defined, and now we can ask, what is this number for specific hypergraphs, right? For graphs, by Turán's theorem, we know the Turán density of cliques, and actually by the Eddington-Shimonovitz theorem, we know it for every graph. Okay, so just depending on the chromatic number of some graph F, we know what the Turán density is. So we might wonder, do we have such a general theorem for hypergraphs? And the answer is no. And even for very simple hypergraphs, this question is still open, and it's still open since the original paper by Turán in 1941. So a problem you could run in 1941 is to determine the Turán density of the three uniform clique on four vertices. Okay, so this is sort of the simplest possible example that you could think of as a generalization of Turán's theorem for groups. Okay, so how does this graph look like? We just have four vertices, and now all of the three tuples form edges. So this edge, this, and this. Okay, now you can't recognize anything anymore, but I guess it's simple enough. So we have four edges, and we still don't know the Turán density. And in fact, as we will discuss in a moment, we don't even know it for three edges on four vertices, so the K4 minus. Okay, but let's first talk a little bit about this one. So so we can consider the following hypergraph. We have three partition classes. Each of these is of size roughly n/3. So since we only care about the asymptotics, it's not really important whether we have the divisibility or not. And we place the following edges. So all edges of this kind, which intersect each of these three partition classes, and then all edges which are of this type, or this type. Okay, so always two in this partition class and one in this, then two in this partition class, one in this, and two in this partition class and one in this. So this three graph is K4 free. So why is this? Imagine that we have the K4, so in one of the partition classes, we would have to contain at least two vertices, but also not more than that, because our K4 contains an edge on any triple, and we don't have any edges inside each of these. So we have two vertices, let's say in this partition class. But then since the other vertices need to be in a different partition class, they must be either here or here. If we have one vertex in here, we are missing the edge from these two to that vertex. So both need to be in here. But if both are in here, then we're missing the edges from these two to any of these. Okay, so this one is K for free, and it has roughly 5/9 and choose 3 edges. Okay, and the conjecture is that this is best possible. Okay, so this is, as I mentioned, open. But we do have some small observation that, and this is not the best possible bound, but it's maybe a nice first example for some of the methods and the arguments that we can do for these kind of problems. So the extremal number is at most 2n minus 3 divided by 9 times n choose 2. So this is sort of an oddly precise thing, but the thing that we care about more maybe is that the Turán density is at most 2/3. So by now we know much better bounds for this, but many of these are obtained with flag algebras, which we will not talk that much about during this course. And again, this is a nice first example for the type of arguments that we will see. Maybe actually I can. Okay. So the only observation really that comes in is that if we look at any edge, and a vertex outside, then we know that one of the edges that this edge, this vertex forms with the pairs of vertices inside this edge has to be missing. Okay, because otherwise we would have one edge plus the 4 edges that are formed by these, plus the 3 edges that are formed by these 3 pairs and that vertex. And that would be a K4. So that will give us a bound on the sum of the pair degrees. So the number of edges that this pair is contained. So given 2 vertices in H, let d xy be the number of z such that x1 z is an edge. Okay, and this we also call the pair degree. So now let H be K4, 3, K-graph and vertices. This means, because of this reason, that for every edge x, y, z, of H, we have that when we sum this number for all the three pairs, then we are bounded. So dxy plus dxz plus dyz. It's at most, and what is it at most? So as I said, for every vertex that we take outside, we have at most two of the edges from some pair in here to that vertex. So n minus 3, the vertices outside, times 2. Okay. Okay, so now let's sum this over all edges in H. So x, y, z, and H. Okay, so this is at most the number of edges in H times this. And on the other hand, so what is this sum? How often does, when we look at all the summands of this sum, how often does this term appear? So it appears whenever xy is contained in this edge. And how often does that happen? That's just the definition of this number. So this term appears dxy times overall in this sum. So we have that this sum x, y, z dxy dxz is equal to the sum taken over all pairs. So this is how we denote the pairs of vertices. So the two sets of the set BH and xy squared. Okay. So when we see this, we want to apply convexity. Okay, so we get n choose 2, and then the sum of these dxy divided by n choose 2, and this thing squared. Okay, and now again, by double counting, what are we actually counting here? So for every pair xy, we count the number of edges that xy is contained in. So in some sense, we're counting every edge, but we're counting every edge from each of the three pairs that are contained in that edge. So we're counting each edge 3 times. So this is n choose 2, then 3 times the number of edges of H divided by n choose 2, this whole thing squared. Okay, so then one of these cancels out. And we have 9 number of edges of H squared divided by n choose 2. And so now we compare this thing with this upper bound. So have that number of edges in H times n minus 3 times 2 is greater or equal to 9 times the number of edges H squared, n choose 2. And this, so canceling out one of these numbers of edges, we get n minus 3 okay, so here actually we count this for all the edges on the outside, but we also count 3 times that edge itself, right? So because for each pair we also count this edge. So here we will get this plus 3, right? So this term are just the outside edges, not including this edge itself. But we also, for each of the pairs, we're also counting that edge. So that's 3 times. So this thing here is 2n minus 3. So here we have 2n minus 3. And so that gives us here 2n minus 3. And so now canceling out, this gives 2n minus 3 divided by 9 times n choose 2. It's greater or equal to the number of edges. Okay, so sorry about that. So this gives us the an upper bound on the number of edges in H if H is K4 free, and then clearly this number gives that the Turán entities at most 2/3. Okay, so then as I said before, even for the K4 minus, we don't know its Turán entity, but maybe let's go through the same game. So let's give some construction that gives us a lower bound, and then let's say some basic simple argument that gives us some upper bound. So this example is due to Frankel and Purity. And so this example is a little bit more complicated. So define iteratively hypergraphs, street graphs. HI. So H1 is a hypergraph with 6 vertices. And so if I draw all the edges, it will be maybe a bit too messy. So let me say that we're looking at this vertex, and we want to see which edges we want to place for that vertex. So we'll place these edges, but now we rotate the whole thing. Okay, so for every vertex, we will place these edges. So in particular, we will have that any 3 consecutive vertices of this outer 5 vertices will form an edge. Okay, so we also have this edge, we also have this edge, and then we're back here. Okay, and for the crossing ones, so for this vertex, we also have this edge. Okay, so if I want to draw all the edges that this vertex will eventually be contained in, we also get this edge and this edge. Okay, and now maybe you see why I didn't want to draw it in the first place, because now you can't see anymore what I meant. And now, what is the hypergraph HN? The hypergraph HN, so we take 6 copies of HN minus 1. Each of these is a copy of HN minus 1. And also in the center. And for the crossing edges, we place the same edges as we did here. Okay, so again, and I will now only draw this that we get it with the rotations. So we also have these edges, these ones, and then again we rotate, which in particular means that we also will end up seeing this edge and this edge. Okay, so and this type of construction is also called an iterative blow-up construction. So in each step, we take what we had on the previous number of vertices, we take and then we take a copy of that initial construction, but where each vertex is replaced by a previous copy, and on top of those, for the crossing pairs, we again place the edges that we saw in the first step. Okay. So this example this is K43 minus 3 and has density roughly 2/7. And this is conjectured to be best possible, and there are some bounds obtained with flag algebras that get very close to this. So why are we K4 minus 3? So for K4 minus, any 2 vertices are contained in an edge together. So by hand, you can check that this H1 is K4 minus 3. And then when we are in a general step, so either all the vertices are in different partition classes, but then it follows from the fact that this one is K4 minus 3. And if we have 2 vertices in the same partition class, then so if we have a third vertex that's also in here, so that we make use of one of the edges inside this partition class, then we also get that each other vertex must be in here, because otherwise, so these 2 vertices are contained in a pair, but only if that vertex that they are contained with in a pair lies in one of these other partition classes. Okay, so that if we have one vertex outside it and one vertex in, so one vertex in here, one vertex in here, it means that we need to have another vertex outside, but having another vertex inside here means that we need to have another vertex in here. But that would mean we have 5 vertices, but we only have 4. Okay, is that clear? Some faces look question. Okay, so we say all vertices are in here, it follows by induction. If all vertices are in different partition classes, it follows from the first step. So we need to have some vertices which are in the same partition class and some vertex that's not in the same partition class as these. But then because this vertex together with a vertex in here must be in an edge, so the vertex that they are in an edge with must now be distributed somewhere in these other partition classes, because we only have those edges. But so we have one other vertex in here, but for these two vertices to be in an edge together, we must have one more vertex inside here, and then we have 5 vertices. Okay. So now let's look at some small argument that tells us that the Turán density of the K4 minus is at most 1/3. And so maybe before then, can we say a very simple argument that the Turán density is at most 1/2? So if we have some hypergraph H with density on some large number of vertices and with at least 1/2 plus epsilon density, then why do we need to have a K4 minus? Yeah. So for the 1/2 bound. So one of the vertices, if our density is larger than 1/2 plus epsilon, one of the vertices needs to have degree 1/2 plus epsilon. So there exists B with the degree of B maybe larger than 1/2 plus epsilon times 10 choose 2. Okay, and so we will see in a moment that this is sort of a general argument. So in some sense, the neighborhood of this vertex in a hypergraph we call link, and we can denote it by this. So this is our vertex V, and we place edges here whenever this pair together with this vertex forms an edge. Okay, and this degree now means that this graph, right? So this is a 2 uniform graph, and the density of this is at least this. So, but then by Turán's theorem, we find a triangle in there. And that means that these 4 vertices have span 3 edges, and that hypergraph is unique, and it's the K4 minus. Okay, so this is a very simple argument why 1/2 works. So let's see why we have 1/3. Okay, so let's count the number of 4 sets of vertices on which we have exactly 2 edges. So let S. Right. So let H be K43 minus big graph. And let's for later denote the number of edges as some alpha times n choose 3. So we want to show that this alpha must be asymptotically below 1/3. So again, as always on n vertices. And now let S be the number of 4 sets of vertices that span exactly 2 edges. So then we have that this is just the size of the neighborhood of x and y, choose 2, and then summed over all pairs x, y. So why is this? So we know that because we have k4 minus 3, so on any 4 vertices, we have at most 2 edges. And with this thing, we count any, right? So we take 2 vertices x, y. And now we look at all choices of 2 vertices such that we have these edges. So definitely we count each of these 4 sets with exactly two edges. Definitely we count each of those once, but we actually also don't count them more than once, because each of those in this way we only count from this pair. And there's just one such pair, because otherwise we would have more than 2 edges, which would imply k4 minus. Okay. So by convexity, we get that S and this is at most n choose 2 times the sum over all these dx y divided by n choose 2 and then choose 2. Okay. Now this thing, as we saw before, when we sum over all pair degrees, we get 3 times the number of edges, because we count every edge from each of its 3 pairs. So this is n choose 2, then 3 times the number of edges of h divided by n choose 2, choose 2. Okay, now let's plug in our alpha and choose 3 for EH. So n choose 2, 3 times alpha and choose 2. Alpha and choose 3 divided by n choose 2, choose 2. And okay, so now, because we're only interested in the asymptotics, so let's just put a big O of n to the 3 here, and just see what we roughly have here. So this thing here is essentially n cubed divided by 3 factorial. The 3 cancels with this 3. So then we have alpha n times n choose 2. The n choose 2 cancels with this. So we have alpha n choose 2, which gives alpha squared n squared divided by 2. Here we get another n squared divided by 2. So this is alpha squared n to the 4 divided by 4. Okay, and we have this error. And okay, so this gives us some lower bound on that S. So we want to get an upper bound, And this we do by double counting the number of pairs TE, where T is one of those four sets of vertices on which we have exactly two edges, and E is one of the two edges. So where T is a four set spanning, so four set of vertices spanning exactly two edges, and E is one of these edges. So then this, if we want to count it in terms of S, we just get 2 times S, right? For each of those sets that we counted with S, we have 2 choices for E. So 2S. And on the other hand, we can just count from one edge, and then the number of vertices that we can extend this edge to such a set T, right? So we start with an edge, and now we want to pick another vertex. So this at most the number of edges in H. And then in the worst case, we can extend this edge with each of the vertices. Right? Some of those might not span two edges, but this is an upper bound. So then we combine this thing with this thing. So so we have alpha squared n to the 4 plus big O of n cubed. This was the upper bound on S, and the sorry, this was the lower bound on S, and the upper bound is, so this number of edges of H, which is just alpha n choose 3 times n minus 3. And okay, so then here we essentially just have alpha.
Half this one.
Sorry.
I think almost half of this one because it's 2x.
Yes, thanks. And so then we solve this for alpha, and we get that alpha is at most 1/3. Okay. Okay, so this gives a simple bound for our K4 minus, but again, this bound is not really best possible from what we know nowadays. But again, these kind of arguments appear quite frequently. So
I have a tricky question. Looking at S seems natural, but the last step looks a little bit tricky, right? I would have done a very stupid thing. This is at most n choose 4, then S is at most n choose 4, but the bound would be really bad. So is there a reason of considering this pair?
I mean, so a reason as in like what would be the intuition for this? I mean, I guess so. I guess it's quite natural to start with these 4 sets, right? Mm-hmm. Because exactly as what you said, if we just double count by counting the 3 edges that we see on any 4 vertices, we get the band bound. But I mean, I would say that okay, if you then play around with this, it's but yeah, it is a nice argument, right, for being so short. Yeah. I guess it's difficult to say like because that's the trick somehow, right? Yeah. So let's now move to the first result where we can actually determine the Turán density of a K-graph. And this is a surprisingly general result. Like given that we hardly know anything for these small K-graphs. So we will characterize those K-graphs which have Turán density 0. And for this, let's first define what exactly this characterization will be. So a K-graph, let's say H is K-partite. If we can divide partition the vertex set such that every edge is crossing. Okay, so we partition into K parts and every edge is crossing. If there is a partition of the vertex set of H, it would be 1 to be K, such that each edge of H intersects each PI. Okay. And let's also maybe note down one example because it will come up in a moment. So we can now, right? So this is just a generalization of bipartite to hypergraphs. And let's denote the complete K-partite K-graph with different sizes of the partition classes. So the sizes we put in the indices. And K is the complete K-partite K-graph with its partition classes. Name sizes M1 to MK. Okay, so we have some number of partition classes. One is of size M1, next M2, M3, and so on till MK. And then we have all edges which are crossing this way. Okay, and so this very nice result due to Erdős tells us that the Turán density of a K-graph is 0 if and only if it is K-partite. Okay, so yeah, again, it's sort of surprising that on the one hand, for very small specific, even 3 graphs, we don't know the Turán density, but then we have the characterization for all those of Turán density 0. And okay, so let's prove this. So first, one direction is quite simple, right? So if f is not k-partite, and it's not contained in the balanced complete k-partite k-graph on n vertices. And this one has density roughly k factorial over k to the k. Okay, and yeah, so this being positive. Okay, and so this balanced complete k-partite k graph is just this one with all these mi being essentially the same size, and of course divisibility. So we cannot guarantee necessarily that they're always exactly of the same size. But for the Turán density, we only care about the asymptotics, and therefore we get this density. Right. So in particular, this theorem tells us that the Turán density of the k graph is either 0 or at least this. Okay, so we have this interval between 0 and this number, in which there's no Turán density of the k graph. Okay. For the other direction, okay, so we want to say that if we now take a k-partite k graph f, then the Turán density of this one is 0. And for that, we need some definitions. So, and these definitions are important in general. So try to remember them. The first is essentially the definition that we sort of considered already in this example up there. So for k graph H and a vertex B in H, the link of H at this vertex is sort of the projection of H from the perspective of this vertex, right? So we place an edge whenever together with this vertex we have an edge in H. The link H at V and we usually write it H sub V is the k-1 graph on the vertex, the same vertex set. With edge set. So we place all those k-1 sets as edges, which together with V form an edge in H. So V union E is an edge in H. Okay, so for a 3 graph, we would have that for vertex V, this is just a graph where we place an edge here whenever this was an edge in our 3D. Okay, so this is the link of the vertex. And then we also want to look at homomorphisms. So a homomorphism from a graph F to K graph H is a map from the vertex set of F to the vertex set of H that preserves edges. So this is just the set, the set of images of all the vertices in E. And the number of homomorphisms we denote by hom FH. And then we also care for the homomorphism density. So that's just the number of homomorphisms divided by all possible maps from F to H. So T F H, the homomorphism density is hom F H divided by 2 H to the B F. Okay. So now going back to the proof, we first want to show a plane that's maybe also interesting by itself, and that's the main step of the proof. So for every K graph H, we have that the homomorphism density of this the complete K-partite K-uniform hypergraph with partition classes size or size of partition class M1 to Mk. This homomorphism density into H is at least the number of homomorphisms from just taking K-uniform H here into H and then raising it to the power of the product of these. So homomorphism density H and then the product of the MIs. Okay, and so this thing here is really just an edge. Yeah, just a K-uniform edge. So let's prove this. We do induction on K. And K equals 1 is easy to like. So let's do the induction step. And so we will, in the proof, we will often switch between the homomorphism density and the number of homomorphisms. So let's start by actually computing the number of homomorphisms K M1 into K into H. And okay, so the idea here is that we want to use induction, right? And so what we do is, if we have our different partition classes, and here maybe we have H, we first want to pre-embed one of the partition classes. So let's say here, we first map these arbitrarily, right? Because we are looking at homomorphisms, so we might even map several of these vertices to the same vertex. We just embed them in some way, and then we look how many possibilities are there to extend that to a homomorphism of this whole thing into H, right? So in order to do that, what we then need is that we want to embed now this K-1 uniform thing on a partition class of size M1 to Mk-1 into, and now not H, because not everything is eligible now to be embedded, because we want that whenever we embed something here, it needs to form an edge together with those vertices into which we embedded, or to which we embedded this last partition class. So in particular, any edge here needs to be embedded into an edge in the link of in the intersection of the links of these vertices. So if here we have, so let's say this is V1 would be K, then here we want to embed every edge into the intersection of these links. Okay, so we sum over all potential embeddings for this last partition class. And then the number of homomorphisms that we can embed this K-1 uniform, these partition class sizes into the intersection of these links. Okay. And now we switch back to the homomorphism density, because now, of course, we did this so that we can apply induction. So this thing is just we pull out this factor n to the m1 plus up to mk-1, and then here we see the homomorphism density of this into the intersection of these links. Okay, so now by induction, this is, so this first part remains the same. And then here we get that we can replace this by the homomorphism density of a K-1 uniform edge into this intersection of the links to the right power. So T K-1, 1. And to the power of M1 times up to K-1. Okay. And so then, as we saw several times already today, again calls for convexity. Okay, so we get another factor because we sum here over all mk. So and since these can be the same over all choices of vertices of H with repetition, like pick with repetition, and we want to pick mk of those. So we get another factor of n to the mk to the front. So now this is n to the sum over all these mi's. And then inside here we have this t k minus 1 h e, and this thing we divide by n to the mk, and that whole thing to the power of m1 minus m2. Okay, so this already looks nice because we have this factor here. In the beginning, we computed the homomorphisms, but what we're interested in eventually is the homomorphism density. So we can divide by this on both sides, and we get here the homomorphism density. And here we get this structure already to this power. So basically what we want is we want to estimate that this thing is at least the homomorphism density of a k-uniform edge into H to the power of mk, right? So, but to estimate that, let's again actually consider the sum of all these homomorphisms, numbers of homomorphisms. So, sum over morphisms, one. Let's estimate this. All right, so what do we do here? We count the homomorphisms of an edge into some hypergraph. Okay, so both hypergraphs here k-1 uniform. And so what is that? Basically, we just count the number of edges in this hypergraph, but because we have different mappings for each ordering of an edge, right? So this actually counts every edge k-1 factorial times. So let's take that k-1 factorial out. And so now let's count in the opposite direction. So here we sum over all the tuples of v1 to vmk. Instead, we can also, right, but then we just count the number of edges in this hypergraph. So instead, we can also sum over all k-1 sets of vertices and ask how many tuples v1 to vmk do we have such that this k-1 set is an edge in the intersection of the links. So we sum over all k-1 sets, and we ask what's the number of tuples v1 to vmk such that E is an edge in each of these links. So such that for all I, E is in H. Okay, so now that number is just the same as we look at, okay, for how many vertices is E an edge in the link? And then we take that to the power of mk, right? Because these can be the same. So okay, and now again, this situation calls for convexity. And so we have our K minus 1 factorial still. Then we get an n choose K minus 1 out here. And we get the sum over all E, the number of B in EH, such that E is an edge in the link of B. And this divided by n choose K minus 1, and then to the power nk. So we're almost done with the plane. So now let's just take out the n choose K minus 1. And so we have K minus 1 and K minus 1 to the power of 1 minus mk. And then, so this sum, what do we count? We count every edge, but we count every edge from the perspective of each of its vertices. Right, so we counted k times, because each vertex, each of the vertices of the edge can play this role. So here we have k times the number of edges of H, and this thing, right? So you see that this structure is getting closer and closer to what we want, because we wanted this power here. Here we wanted the number of homomorphisms, which is almost this. So let's now bound this thing by just n to the k minus 1 divided by k factorial. So we have k minus 1 factorial and to the k minus 1 divided by k minus 1 factorial, and that whole thing to the 1 minus. Right, so we go in the right direction because this thing is negative or non-positive. And then we keep this thing here. And then let's take these k minus 1 factorials. So how many do we have of them? We have m to the k of those. Let's put them all in here. So that gives us k factorial. So here we have k factorial e to the h, which is already nice because this is the number of homomorphisms of an edge into h. And in the front here, we have n to the k minus 1 times 1 minus k. And now this thing, so here we actually want the homomorphism density, right? So that gives us an n to the k, but because we wanted that to this power mk, so we lose this factor here, and we're left with n to the k minus 1 plus mk. And okay, so this thing is then n to the k minus 1 plus mk times the homomorphism density of an edge, a uniform edge, into h, and this whole thing to the mk. Okay, now we plug this in to what we wanted to estimate here. So But then, because here actually what we were interested in is the homomorphism density, right? So we divide by another n to the k minus 1. So the sum over these homomorphism densities, k minus 1. So this thing is greater or equal to n to the mk t. Mk. But now, so this thing here is what we have on top here, right? So we divide by n to the mk, which is the factor that we have left here. So what we are left is that this the sum of the homomorphisms in the beginning, 1 mk into h is greater or equal to this thing, so n to the sum of these mi's, and then, so as I said, we plug in this in the numerator there, and so we divide by this n to the mk, so we're left with this, and then to the power of m1 times until mk. So t k 1 h to the product m of the mi's. Okay, and since in the front we were calculating the homomorphisms, the number of homomorphisms, so we divide by this and we get the homomorphism density, and this finishes the claim. Okay, and then next time let's finish the proof of our theorem with the help of this claim, but that will follow quite easily, because essentially what we get from this is that, so if we have a k-partite k-graph f, and we want to show that if we look at some large k-graph h with positive density, we want to find a copy of this f, then using this, and because this is essentially the number of edges, right, or we can relate this to the number of edges in H. So we get that we have a positive, that this homomorphism density of this this k with partition classes size m1 to mk, that the homomorphism density of that is positive, which means that we have the right order of magnitude of homomorphisms from this thing into H. But we can choose these so large that our f is contained in this, because f is k-partite. And but then if we have so many homomorphisms, some of them need to be injected, right? Because if we, as I said, we have a positive fraction of them, so the right order of magnitude, but the degenerate homomorphisms have to map at least at least two vertices on the same vertex, and that means they have a smaller order of magnitude. All right, let's see that tomorrow. Any questions?
Any questions?